Hi everyone, so welcome to this conclusive session of the semester. Uh, I will start right away actually. Okay, so this is first of all a summary of what we have done uh, previously. First is that we have seen that convolution operation that we have been studying over last several weeks. It is actually some type of multiplier. In fact, can be thought of as generalized multipliers. And we saw that when we multiply two numbers, we are effectively convolving their digits, right? And then last time we saw that the reason why that is the case is because any number can be written as a polynomial in power of 10. 121 is nothing but 1 times 10 to the power 2, 2 times 10 to the power 1, and 1 times 10 to the power 0. And so when we multiply two polynomials, by the way, are you able to hear me? And is the screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this we, last time, if you remember, we generalized it. We said that if I have two polynomials, P of Z and Q of Z, and if I convolve their coefficients, what I get is coefficients of the product of these two polynomials. And so one example is when these are given as AZ plus B. And so when I do P of Z times Q of Z, I am doing AZ plus B squared. And I get A square C square plus 2ABZ plus B squared. And so these coefficients A square, 2AB, and B square are what we get if we convolve the sequence AB with itself. Okay, so there is a comment that please share video recording of lectures on the convolution topic. That I have already shared, Chut. If you look at our Google Classroom, I have placed all the videos until the last lecture. Okay. All right. So the last thing that we did, the last Thursday's lecture is, we said that how about if we take the variable z of this polynomial equation to be exponential at some frequency f. And then what happened is that the sequence x of n, the complex exponential sequence as a function of the time index n, ended up becoming what is known as an eigenvector or eigenfunction of the convolution operation. Basically, it comes out undistorted at the convolution output. But it may get scaled, but otherwise it comes out undistorted. The reason why it is called eigenvector or eigenfunction is because in linear algebra, there is actually a property. So I'll just write here. An eigenvector matrix H. Okay, I should say that if vector X is an eigenvector of a matrix H, then what happens is H times X is a matrix vector product. And typically, we put matrices and vectors in boldface, so let me do that. So this H times X, which is a matrix vector product, can be written as some scalar lambda times the vector X, and this lambda is a scalar, where scalar lambda is called the eigenvalue. Okay, so this is several. So you see what happened is that I multiplied this matrix H with this vector X, and typically I don't get X at the output unless X is an eigenvector, in which case what I get is actually a scaled version of X at the output, and the scaling factor is called the eigenvalue. So something like that is happening over here. We send X as the input to the convolution operation, and what comes out at the output is the same X, the same complex exponential, except that it gets scaled. And we saw last time that the scaling factor is nothing but the Fourier transform of the impulse response of the LSI system. Okay, so this is sort of like, I would say this is this H of F, which is the Fourier transform, is sort of like eigenvalue. Okay, so this is what we saw last time. It is really quite an interesting aspect of the convolution operation that makes it so powerful. And so now what happens is that if I write any input signal to the LSI system as made up of a summation of some scaled complex exponentials at different frequencies, meaning by this type of summation, these are complex exponentials at frequencies f of k, and they are getting scaled by this complex valued scalar multiplier capital X of k. Then what we have observed here, it happens for individual frequencies, meaning that for each of these complex exponentials, the effect of this LSI system is to further scale it by the frequency response of the LSI system at the frequency f of k. So this again we saw the last time. Okay, if you are fuzzy about it, then I suggest that you go back and take a look at these slides that I have already posted. Okay, so this is something that we want to further expand upon today. But before we do that, let us consider continuous time signals as well. So this is how we have written the input to the LSI system. Remember, on the previous slide, we said that input can be written as scaled exponentials. This is the complex exponential. It is scaled by x of k. And the input is written as the linear superposition of all of these scaled exponentials. Who can tell me what these weighting factors are or what the scaling factors are, x of k?
Sir, e raised to minus j 2 pi n 2 pi fk into k into h of k.
Harsh, there is no h here. This is just
Sorry, yes, sir.
all I'm asking is how have we defined this capital X of k, this weighting or this scaling parameters?
So it
What
should
have
be
we
only e raised to
ft of x of n.
Yes, Fourier transform.
Fourier
These are the
transformation factor.
Fourier transform of x of n. Fourier transform of x of n at frequencies
fk.
f of k. If you change f of k, you will get a different value of x of k. And so in the continuous time, the integral becomes, the summation becomes integral, and you don't have discrete frequencies f of k anymore. You don't have discrete time index n anymore. Everything becomes continuous, but the formula remains quite similar. X of k becomes x of f. This is the Fourier transform evaluated at frequency f. This complex exponential, which is a function of discrete values f of k and n, it becomes a function of continuous values f and t. Summation turns into integral, and therefore I have this df notation. We also saw that if I look at the output of the convolution, which is y of n, which is x of n convolved with h of n, which when x of n can be written like this, we have seen that it can be written as the original Fourier transform x of k, which is getting further scaled by h of fk. The Fourier transform of h of n evaluated at f of k. So if I convert this whole equation into continuous time, again, n will get replaced by t. K and f of k will get replaced by f, which is continuous frequency. And then summation will become integral. And so then this becomes the formula in the continuous time. I have labeled them as equation A and equation B because maybe we will need these equations later on. Okay, so we already have defined the Fourier transform and inverse Fourier transform, but maybe let us recap or review the definition one more time. So if I have any discrete time sequence h of n or x of n, its Fourier transform is defined like this. This is this summation. Summation is over m. And m can go from minus infinity to infinity, or if h is finite in extent, then it will go over only those values of m over which h is non-zero. This part here is the complex exponential. And this is the actual sequence whose Fourier transform we are taking. And this summation it can also be written as vector dot product. So this circle means dot product. So effectively, when we compute this Fourier transform, we are effectively taking the dot product of the vector h, the actual sequence whose Fourier transform is being taken, and the dot product is with respect to a vector E of f complex conjugate. And E of f is a vector made up of this complex exponential samples. And in the last lab that you did, we had defined this G matrix, which was made up of many different columns. And each of the column was essentially one vector E of f at some frequency f. So this is called discrete time Fourier transform, because we are in discrete time domain. So again, by the same process where we replace summation by integral and indices m and f by continuous counterparts, we get the continuous time Fourier transform, or it is just simply the Fourier transform equation. And this formula here, you may recall when we did those functions g1 of t and g2 of t, or g in phase of t and g quadrature phase of t, those are the continuous time functions. We had said that this type of evaluation is continuous time counterpart of vector dot product. Okay, so this is what we have seen earlier. Okay, and then finally, to get, if we are given this h of f, the Fourier transform, we can get time domain signal by doing inverse Fourier transform. And this inverse Fourier transform can be thought of as synthesis operation, whereas Fourier transform can be thought of as an analysis operation. Alternatively, this is the linear superposition view. And this is the inner product view. Okay, so now let us capture begin with that time domain signal x of t, it can be written as linear superposition of a lot of different complex exponentials, where each complex exponential is getting weighted by this x of f. And previously we saw that this observation we had that the output of a convolution operation can be written like this. We have converted it to continuous time in this manner. This was our equation B on an earlier slide. But this y of t here, by the definition of inverse Fourier transform, it can be written like this. This is the definition of inverse Fourier transform that we had on the previous slide. And so if I compare this equation here with this equation, y of t is same as y of t here. E to the power j 2 pi ft df is same as e to the power j 2 pi ft df here. And so therefore we have to conclude that this y of f has to be equal to the product of h of f and x of f. But this y of f, h of f, x of f, we have said earlier that they are the inverse Fourier transform. I'm sorry, they are the Fourier transform of x of t, y of t, and h of t. And so the overall conclusion is that whenever I have convolution operation going on in the time domain, and one way to think of it is that I have some input x, I am sending it through linear time invariant system with impulse response h of t, and I am getting the output y of t, which is the convolution in time domain of x and h. In the frequency domain, the effect is as if I did a multiply operation. I take the Fourier transform of the input, x of f. I take the Fourier transform of the impulse response of the LSI system. And what I get is the output y of f. It turns out to be the product of h of f and x of f. So this is one of the key properties of Fourier transform and of convolution of linear shift invariant or linear time invariant systems whose output can be written as the convolution of the input and the impulse response. It turns out that although you are doing convolution, like you are doing some operation, you are cooking something in your kitchen, it turns out that if you change the viewpoint, you go from time domain to frequency domain, then the convolution becomes something simpler, something that we all understand. It becomes just the multiplier. It's like you're cooking something in your kitchen and you have a kind of a complicated recipe. Whereas maybe if you go to some different kitchen and you try to cook the same thing, the recipe suddenly becomes very simple. Okay, so convolution can be written as we have seen earlier as this summation. In the continuous time, it can be written as this integral or dot product. And what we have seen is that convolution in time domain is equivalent to multiplication in frequency domain. So this is how it happens in the continuous time. And this is how it happens in the discrete time. Now, one thing I want you to notice very clearly is that in the continuous time, the limit of the integration is minus infinity to infinity. Whereas in the discrete time, the limits are minus 0.5 to 0.5. Okay, forget about this. I think we are not going to have time to go over this box. What it says is that, remember we did the square root raise cosine? Why the word square root is used? We can kind of understand through this math, but we are not going to go there. So this is not in the syllabus. But this is an important point, that when we go from continuous time to discrete time, this inverse Fourier transform integral has to be done only over a range of minus 0.5 to 0.5 of frequency variable f. And the reason is that this discrete frequency is periodic and its period is 1 unit. Okay, so very quickly to see that. In discrete time, just hold on. So in discrete time, unlike continuous time, so this doesn't happen in continuous time. Only in the discrete time, the complex exponential so this is my complex exponential j2 pi fn. It's periodic in the frequency variable f with a period 1 unit. So this is very kind of easy to see this. So if I call this as, I'll call it as E of f. This is the complex exponential at the frequency f. What we are saying is that E of f is same as E of f plus 1. And this is same as E of f plus 2. This is same as E of f minus 1. Same as E of f minus 2. And in general, this is same as E of f plus m, where m is an integer. This is easy to see because E of f plus m can be written as, all I need to do is substitute f plus m, where m is an integer, in place of f. But this is same as the original complex exponential at frequency f times exponential 2 pi mn. However, remember that since m and both are integers, this is essentially some integer multiple of 2 pi. So I get this plus j sine, which is nothing but 1, plus j0, which is nothing but 1. So maybe I will delete, however, here I'll just start with since And then I can write here, this is same as so therefore the limits of the integration for the inverse discrete time Fourier transform are minus 0.5 to 0.5. This is the base period. Because everything else then just repeats. So that is something that we have to be mindful. Okay, so that was one topic. Now, actually, I'm going to go over another topic of the Fourier transform. This is actually pretty straightforward. Hopefully, you won't have any difficulty in going over these examples. This is just pure math. So one is we are going to take Fourier transform of a complex exponential which is oscillating at some frequency f of c. So all I do is I plug it, I use this formula for Fourier transform. So this is the Fourier transform formula. In that, I plug in the value of x of t, which is this complex exponential. And you can see how I went from this line to this line. It's just a simple simplification. But you may recall that this part here is our definition of Dirac delta function at f minus fc. This we had done earlier. Let's go to equation 2 on slide 30. This is our equation 2. This is the definition of Dirac delta function. So in this equation 2, if I substitute y t for y and f minus fc for x, then I get the formula that we were just now looking at. So what is happening is that my input signal is a complex exponential at frequency f of c. Just one frequency, f of c. If I take Fourier transform, no wonder I get just a single spike at the location f of c. Remember, this denotes the Dirac delta function located at f of c. This also we had done earlier. So no surprise here, because I have just one exponential. When I analyze it, when I pass it through the Fourier transformer, when I analyze it, that mathematical prism tells me that you have only one frequency and that frequency is located at f of c. So it's very intuitive. There is a math here, but the math is very intuitive. Basically, only when this small frequency, this small f, when it becomes f of c, the dot product becomes very large. whenever f is different from f of c, even if it is slightly different from f of c, the dot product, remember this is the dot product operation, this is the analysis operation. The dot product says that the output is 0. And therefore you get just one spike at f of c. Well, what happens if we multiply this complex exponential by some magnitude a? Well, nothing much changes. The Fourier transform becomes the original delta function after it got scaled by a. The math is very similar. And so now we can see that if my input signal is made up of two complex exponentials, one at f of c, another at minus f of c, and they get further scaled by some scalar a divided by 2j, then I don't have to do the math. I can just use example 2 and say that the Fourier transform will be two spikes now. One located at f of c, this is the one at f of c, this one will be located at minus f of c. Why do I say that this is located at f of c, this is at minus f of c? This also we had done earlier, so let us go back. These are the type of things that may come in your exam, okay? So be aware of it. Remember in this slide we had said, slide number 14, our probably one of the first lectures on Fourier transform topic, we had said that f of x minus x0 is f of x shifted to the right by x0. F of x plus x0 is shifted to the left by x0. And so that's why over here, this is the delta function shifted to the right by f of c, meaning that it is located at f of c. The original delta function is located at f equal to 0. This delta function, maybe I should write it down here. This is located at f equal to f of c. This delta function got shifted to the left by f of c. And so this is located at f equal to minus f of c. And they further got scaled by this complex multiplier. Basically, the Fourier transform has both the magnitude as well as the phase. Okay. So the way to see that pictorially is by this type of diagram. There are two spikes at f of c and minus f of c, and their magnitudes, as we can see from here, if I take the absolute value, it becomes just a divided by 2. So what we did was we took a time domain signal, which was the sinusoidal signal. If I take Fourier transform, its magnitude becomes two spikes. If I take inverse Fourier transform of these two spikes, I get the sinusoid back. Let's do one more example. This is also very, very important type of signal. This is called the rectangular pulse in time domain. See, it's a rectangle. In the time domain, it looks like kind of a box. So it is 0 up until -2 divided by 2. Then it becomes 1. And it goes on until positive t divided by 2. And then it again becomes 0. And so the width of this rectangle is exactly capital T seconds. Turns out that the Fourier transform is easy to evaluate because all we have to do is evaluate this integral. I call this now W of t. Then the limits of the integral become minus t divided by 2 to t divided by 2 because the signal is 0 outside of it. And within the interval, its value is 1. So all I have to do is evaluate this integral, which is straightforward given your calculus course. It becomes this integral. And this turns out to be t times sine pi t f divided by pi t f. This is how it turns out. Okay. But there is this function in the analysis math which says that there is a short form of it. It is called SINC function. It is essentially this sinusoid, except that it is getting scaled by this denominator. And so this is how it looks like. This is, I think, what you have practiced in your lab. So it's a kind of decaying sinusoid. As you go away from 0, this ripples become smaller and smaller. And so now we have another Fourier transform pair. If I take a rectangle and take its Fourier transform, it becomes this type of wavy pulse, which kind of decays out. Okay, and now the last thing that we will do today, in another 5 to 10 minutes, is talk about a very interesting aspect of the Fourier transform, which is called the duality property. I think we briefly talked about it earlier. Basically, what this duality property says is that if you have a Fourier transform pair, from it you can make another Fourier transform pair by just changing the time and frequency. What you were earlier calling time, now you start calling it frequency. And what you were earlier calling frequency, now you start calling time. Okay? And then the other one thing that you have to do is frequency you have to flip. The frequency axis, you have to flip it. You have to do a left-right flipping, which is what this minus f sign tells you. So this is a property of Fourier transform. We are not going to prove this property, but let us make use of it. Remember, we did this example one few slides back, from where we concluded that this is the Fourier transform pair. So now everywhere I'm having f, I'm going to make it t. So this delta of f becomes delta of t. Then in time domain, it doesn't make sense to call this constant as f of c. So I'm just going to give it a new name, which is more appropriate for time domain. This is T of t. So this is a time domain impulse now. It is not in frequency domain anymore. It is a time domain impulse. Who can tell me where this impulse is located at in time domain?
TD.
Coordinate TD.
Yes, Kandharp. So it is in the time domain. If I draw it as a function of time t, this is 0. This is located at some delta t d seconds. Basically, it is the original impulse after I delay it by t of d seconds. And by the duality property, if I take the Fourier transform of it, I get e to the power j 2 pi. Remember, frequency, I have to make it time and time to be frequency, and so I get this equality. Okay, so again, some quick quiz here. What is the magnitude of Fourier transform of delta t minus td?
1.
Yeah, it is 1 at all the frequencies. The magnitude of complex exponential is always 1, no matter what frequency or time we are looking. What is the phase?
2 pi f t minus TD.
Minus 2 pi f td at frequency f. So phase keeps on changing with frequency. And it is also proportional to the delay t of d. And then the complex value of Fourier transform becomes just simply cosine of this argument minus j times sine of this argument. So I'm not going to write it here. And by the same duality, we can say that just like what we saw earlier, that if I take two signals in time domain and convolve it, the effect is as if I multiplied their Fourier transform. And so if I flip that theorem around, then I can say that if I have two time domain signals and if I multiply them in time domain, and then I go and see what is going on in the frequency domain, it would turn out that in frequency domain, their Fourier transforms got convolved. So there is a lot of such type of interconnects that you can make out of this duality property. And so we'll take one example, that if I have this type of signal in time domain, which is basically summation of two impulses, I can write it like this. And this should remind you of the Fourier transform that we had done earlier, except t, the f has become replaced by t, and so on. And so the Fourier transform of these two spikes in time domain ends up looking like a sinusoid in frequency domain. This sinusoid is a function of f now, not t anymore, because we are talking about frequency domain. And how fast it will oscillate in frequency domain, it will get determined by t of d. So t of d is sort of like controlling the rate of oscillations in the frequency domain. Likewise, if I have a wavy decaying pulse in time domain, I don't have to do detailed math. I can right away say that its Fourier transform will be a rectangle in frequency domain. So you get a lot of mileage. You just derive one time and then you can reuse that result subsequently. Do you understand how I got this Fourier transform relationship? Where did I pull it out of? Yes or no?
Yes, sir.
See, we had already derived this relationship. All that I'm doing is, because of the duality property, I am moving this rectangle on the frequency side and this pulse on the time side. And the duality property says that the relationship will hold. That is what I have done here. I also flipped the frequency side left to right, but it doesn't change anything because this is a symmetric signal around 0. So even if I flip it, it still looks the same. Another very interesting aspect of the duality property is that if I shrink or expand the pulse in the time domain, the frequency domain, exactly the opposite thing happens. So here I have a short pulse whose duration is only 1 second in time domain. It's a rectangular pulse. And so in frequency domain, I have a spread out SINC shape. And the spreading is by as much as 2 seconds, at least. The first time the pulse becomes 0 is at plus minus 1 second. So this is the SINC pulse Fourier transform of this narrow rectangle in time domain. If I make the time domain rectangle to be bigger, wider, so I made it 10 times larger, 10 times wider. Then in frequency domain, the pulse shrinks. Where it was crossing 0 at plus minus 1, now it will cross at plus minus 0.1, inverse of this t. And so you can see that the pulse became narrow. So if I expand the width of the signal in the time domain, the width in the frequency domain shrinks. Or the other way is also true, that if I shrink the width of a time domain signal, then the frequency domain width kind of expands. And then maybe this is the last thing we will do today. Remember, we had talked about the modulation theorem. So we will be doing a short proof of it. So this is what we have already seen just a while back. No, sorry, we haven't seen this, but sorry. So what I meant to say is that we have already seen this modulation theorem, that if you have a time domain signal x of t, and you multiply it by complex exponential at frequency f of c, the Fourier transform gets shifted to the right by f of c. And so now if I replace f by t and t by f by the duality property, the same statement I can write like this. So this is the dual of the modulation theorem. So let us first prove the dual part, okay? See, x t minus td is same as x of t convolved with a Dirac delta function located at t of t. This is from the shifting property of the Dirac delta function that we have seen again on slide 30 or 14. Okay, so this is coming from the shifting property. Maybe go up slide. This is the property, shifting property. Okay, even that time we had said that this we will be using to understand the modulation. If I have a function, if I convolve with the direct delta function at x naught, the effect is that the actual function shifts to the location x naught, and that is what we had demonstrated by this picture. So what I will do now is I'll take a Fourier transform of this convolution operation. But remember, convolution in time domain is same as multiplier in the frequency domain. So x of t, Fourier transform is x of r. Delta t minus td, its Fourier transform is exponent at negative j2 pi ftd. This is the example one that we have seen few slides back. So this convolution got turned into a multiplier. And that is the proof of this first statement, the dual of the modulation theorem. And therefore, you can either prove the second statement, the actual modulation theorem, simply by invoking the duality property. Or you can prove it using the same two steps that we did here. The other thing about this property of convolution is that this rectangular pulse is very, very common. Okay, so what happens sometimes is that you have a desired signal and you receive it in presence of some unwanted signal. And so what you want to do is to get rid of unwanted signal, you take this actual signal and you multiply it with what is known as a rectangular gating window. Basically, it's a window which just lets you see the desired part and it blocks out the unwanted. This is called gating or windowing or filtering, etc. And so the communication system, we have our desired signal in frequency domain, which is located over certain bandwidth. But there is a lot of out of band nodes. And so what we do is we multiply in frequency domain the received signal with this gate, which is given in the green. And this is called ideal low pass filter, because it will reject all the high frequencies. It will only pass the low frequencies at which the signal is present. Remember, this is the spectral diagram. This red here is the power spectral density of the white noise. The reason why it is called white is because its power spectral density is constant, irrespective of the frequency. So this is a frequency domain diagram, and I'm doing this gating in the frequency domain. And therefore, what do I need to do in the time domain? Therefore, in the time domain, we need to do what? Blank.
Filtering by SINC pulse.
Yes, Kandar, but what is the name for that filtering? the received noisy signal. R of t, and the inverse Fourier transform of the rectangular pulse, which is as conserved by the thing. What should be this fill in the blank? In the time domain, I am multiplying their Fourier transforms. So in frequency domain, I need to do what?
Sir, convolution.
Convolve. And so the block diagram looks like this. I have some received noisy signal R of t. I pass it through an LSI system, or LTI system, linear time invariant system with impulse response h of t. The output I get is y of t, which is h of t convolved with R of t. And this h of t is to be SINC pulse. And that is called the ideal low pass filter. It will remove all of this noise which is outside of the band. So this would be the last slide of today, last slide of the semester, etc. I hope that you are able to hear this. Did you hear this word with? Yes or no?
No, sir.
Is it audible?
No.
No, sir.
Okay, then we can't do this example. But what this example say, and I'll put this slide on our Google Classroom today, and then you can listen to this on your own. So this is the a bird's tweet. Okay, you will hear the sound of a bird chirping. The second one is the noisy tweet. So basically, bird's tweet has, in frequency domain, it occupies certain bandwidth, and that signal got added by a lot of noise. Maybe the bird is tweeting on a highway where a lot of trucks and heavy vehicles are driving, and they are making a lot of noise. And so if you play this noisy tweet, can't make out that there is any bird here. And then the last one is obtained by doing this. I took the bird's tweet with a lot of noise, and I pass it through this SINC filter, SINC pulse. I convolved it, simply just convolved it in MATLAB. And then if you play this audio, you will see that all of this other noise which was outside of the band of the bird tweeting, it got zeroed out, because in frequency domain, the Fourier transform of the SINC pulse, which is this rectangle in the green, zeroed out all of this other out of band noise. And so surprisingly, this is very clean, almost like the original tweet of the bird. Okay, so that is all. just say a few things at the end that, this semester was very, very much unlike any other semester that I taught in. Well, maybe your previous batch was also like you all, but there is a difference. Your 1 year senior batch, I at least met them in the campus. 1 year ago, the semester started at the normal time in January, and then the on-campus classes were held January, February, and until middle of March. And it was only in the middle of March of 2020 that the pandemic started, and then the campus was shut down. So effectively, you are the first batch that I have taught without meeting any of you. Okay. So it is quite a unique experience in some sense. Still, I hope that through this course, you have taken away a few things, maybe, or maybe mostly through the lab sessions. If you have done your labs very well, and if you've done your project well, then you can be assured that you have taken away some good skills and some good concepts with you, and hopefully they will stay with you. What I have tried to emphasize throughout this course is that the communication theory should be actually called how to make a machine intelligent theory. Okay, because that is what we did by writing MATLAB programs and sometimes C++ programs or Python. We took a bunch of transistors and a bunch of electronic equipments, and we made them behave like how the human brain forms beliefs and how it does this Bayesian mathematics. And that we carried forward all the way to the analysis and synthesis aspects of the Fourier transform. We said how our eyes see the color, or how our ears recognize that this is a piece of music, or this is the high pitch of a train coming closer to us, the Doppler effect, so to speak. All of this are happening in our brains because of effectively the analysis that is going on inside our minds. So with this course, hopefully you have opened your eyes to some of these concepts that will help you in, as I said at the beginning of the semester, should help you in machine learning. It should help you in signals and systems. It should help you also in the probability theory course that you will take later. Some of these topics, like the Fourier transform topic, will be useful in the analysis and development of algorithms course that you will take. The view that we have taken in this semester is mostly what is known as the physical layer. When you take computer networks course, you will see that how this physical layer gets augmented, or how it gets added by several other layers of a communication system. So that will be your computer network course, where you will see the functions of the data link layer, or transport layer, or internet protocol layer, etc. So we have covered quite a bit of ground. I think even this last thing that we did, the modulation theorem of Fourier transform, that will become kind of the central mathematics or central concept when you take analog communication and transmission line theory next semester. Not as much for transmission line theory, that is a whole new subject. But the analog communication, which we didn't get time to do much at all, especially the amplitude modulation or AM, most of it is just this modulation theory. Okay, so hopefully we have covered the ground here in this course, which will help you germinate your seeds in your future semesters. And also hopefully later on, if you pursue career in estimation, detection, machine learning, signal processing, etc. Some of the concepts that may seem little remote to you today, you may feel that I'm still not very good at it, or I'm not very comfortable with it. Maybe concepts of the Fourier transform, or how the convolution in time domain becomes multiplication in frequency domain. If there are certain topics that you are not comfortable with, it is fine. Okay, because whenever you come across a new subject, a new topic, it's like hearing a good song. You know, sometimes what happens is you listen to the song first time and it doesn't resonate with you. Only after the fourth or fifth time you start liking the song. So if some of these topics didn't quite resonate with you in this semester, at least you have become aware of them. And maybe when you learn these topics later on, you will start better appreciating the music that you are listening to. So with that, I will conclude the semester. I wish you all the best. Don't be strangers after the campus reopens. Do come and stop by my office. I want to meet all of you and see how things are going with you. But before that, as you know, within a few days, maybe 10 days or 12 days, we will be meeting face to face when you make your project presentations. So until that time, goodbye, and wish you all the best with your exams. If you have any questions, you can ask now, or else I will